Okay, and thinking of C rates, I probably should have wrote it like this. Like a C1 rate of a 45 amp hour battery is 45 amps. And then I could say the C.1, because this is easy, is for 0.5 amps. So then the C2, which is going this way now, is going to be more amps, so 90, twice as many there. And then the C.5 would be, 22.5? Should have used 50, damn it. 22.5 amps. So if you can run it linear like that, I think it would make more sense just to look at it like that than to have it go C1, C2. I did it. So anyway, okay. So we got the hydrometer thing done. We got the power rating thing done. I did mention cold cranking amps. I don't believe it's on any of the FA stuff, just so you know what it is. So let me see. It's the amount of current available for 1 minute. It's the starting capacity when the battery is cold. So, and the discharge rate is not linear, just so you know that. Like if the C1 rate is truly, I have an example of a battery where the C1 rate is truly 10 amps. That's for 1 hour. Then what is it for 0.5? And you would think it would be 20, but it's not. It's really 17 amps. You start losing stuff. And then for 60 seconds, half hour. Why would I lose you? 1 hour, you get 10 amps. How many are you going to get in half an hour?
17.
How,
Theoretically 20.
Theoretically, you could select 20 in half an hour. Yeah. Okay. 1 times 10 equals 10. Half times 20 equals 10. And see, everything should equal 10, but it doesn't. You keep just yelling out, you lost me. Am I losing you because I'm saying stuff or because you're not paying attention?
No.
Okay.
I'm paying attention.
Okay. So the half hour rate in theory should be 20, but it's not. It's really only about 17 hours. This is out of a Gill book. And for 1 minute, you would think that it would be, wow, it would be 60 times, so it would be what?
10, 600?
600, but it's not. It's 115 or so. 150. So it's not linear. So don't try and make it linear. Okay, temperature, we talked about that. 1.3, I do have those notes, if you care. 1.300 specific gravity freezes at negative 95 F, and 1.1 freezes at plus 19 F. Big difference. When water is added to a cold battery, always place on a charger. You don't want ice forming in there. Water not mixed with acid, and water not mixed with acid will freeze. All right, lead acid charging, or any kind of charging, because I'm running out of time. So when we talk about charging, there are really 2 methods: constant current and constant potential. In a constant current, you set the amps and voltage varies. And this one, you set the volts and the amps varies. So, as an example, all those batteries that I keep bitching about that are brand new that are ruined. And those are pink, so they're Gill. So the Gill, you open up the manual and it says to place this lead acid, it's a sealed battery. To place this into service, you should do an initial examination of the voltage on it. And if the voltage is less than, I don't have it memorized, but
Less than 12.
yeah, it's okay, about less than 12, you should place it on a charger at 14.8 volts. Well, it's a 12-volt battery. Why am I putting 14.8 into it? Because you got to put more into it. And so when I put it on at 14.8 volts, what I should see, I'm going to put it on the machine. I'm going to set 14.8. It's not going to change from 14.8, so it's constant what?
Potential.
It's constant potential. I should see the amps go pretty high. 10, 20, I don't know. And then as it charges, those amps start getting less and less and less and less. And then at some point I'll look at it. I got 14.8 volts because it's never going to change. I should look at the amps and go, yeah, it's only taking half an amp. What should that tell me? It's pretty charged. Okay, so this particular battery, I take it, I put it on the charger. I do that, I look over, and I'm getting 0.1 amp at 14. So I measured it, and I'm at 12 volts or less. I'm 10 volts. Put it on at 14.8, and I look and I got 0.1 amp. What's happening? The battery's broken. That's what's wrong with it. It's not allowing any amps to come into it. It's blocking them. What could block amps? What could block current? Sulfate. Yeah. So, how old were they? Were they seven?
Mine turned 6 2 days ago.
6 years. Yeah, this printed around the box. He had his birthday. 6 years in the box yesterday. So they're probably lead sulfated. So they've been sitting in the box. So I go ahead and I switch it to constant current, and I say, okay, now it's a regulated valve lead acid battery. I got to be careful. I don't want to put too many amps into it. So how about I just go ahead and turn up the amps, because now I switch to constant current, which means I set the amps and the voltage will do what it wants to do. So I go ahead and I put it on, I dial it up to 2 amps. I look over at the voltage, it's 38 volts. All right, am I killing the battery? It's a 12-volt battery. I'm just charging it. It's okay. That's the constant current method. The volts are going to do what they want to get me the current that I need. So the preferred method for a lead acid battery is constant potential. So constant potential for lead acid. That is the preferred method. Which is a good thing, because what's it going to get once I put it in service inside of an aircraft? Constant potential or constant current? Constant potential. I've got an alternator that's going to put out 14.5 volts thereabout, and that's what the battery's going to get. You're just going to get your voltage, and you're going to take the current that you want, and then when you're done, stop it. So that's what it's going to get. So it works out well in that case. Let me see. That is the preferred method. Battery nears a full charge, amps will be less. Sometimes a battery will not, will not take a charge. This is a result of lead sulfate. Yeah, I guess I was right. I do use only approved VRLA chargers on VRLA batteries. That is not necessarily true. For a while there, they had specific ones. You just have to be very careful not to use a car charger that has a lot of current. So don't do that. Yes, the quick start setting, if you're familiar with that. Okay, I think I covered lead acid. Mostly. What are the big takeaways? Oh, we'll get around to that. Okay. Ni-Cads. Nickel-cadmium batteries. Nickel-cadmium, which is Ni-CD or Ni-Cad batteries. That's how they're going to do it. Why? Why Ni-Cads? Better power to weight ratio. Power to weight ratio. Than lead acid, meaning there's more power for how much they weigh. The CCV is nearly constant. They are much more expensive. We covered that. Yeah, 6,000 to 15,000 when I looked at this. And another reason why Ni-Cads you're going to find in turbine aircraft is you have to consider the starting method for aircraft. So in a piston engine aircraft, it starts just like a car does, in theory. If it's fuel injected, it doesn't. You crank and you crank and you crank and you crank and you crank for some pilots. And then you crank some more. And then you charge the battery and then you crank some more. And then you get somebody who can start it. So fuel injected engines are just a real booger to start. Is that right, guys? Huh?
Yeah. Huh?
Actually, we didn't have much problem, did we?
Boost pump.
Boost pump. Yeah.
Wobble pump.
Wobble pump, boost pump. Because in your car is fuel injected, and you just turn the key or push the button and just self-start, and there it goes. I'm getting off subject now. It's going to take too much time. But anyway, in fuel-injected aircraft engines, you actually have to manage the fuel injection system manually to do it. It's like you give it a little bit, then you gave it too much, then you back off a little bit, and then you start it with a mixture rich. And anyway, it can be a challenge, especially when they're hot. So anyway, but a turbine engine, you're actually going to engage the starter, and you're going to motor up the engine to 10% or more. So you got to get this thing up to 10% power strictly on the battery before you start adding fuel and spark to it. So this thing's really off and running quite a while on its own battery, and then you're okay, now I'll start it. So that's a lot of discharge on the battery. And so you need that constant power. If you try to do that with the smaller lead acid battery, you're going to run out of juice on there, run out of poopy, and then the engine's going to start spooling down, and then you're going to get a hung start or a hot start out of the engine, and then you're going to really be sorry. So Phil will cover that stuff. So you don't want that. I do have in my notes fewer charge-discharge cycles, which would be a problem. Fewer charge/discharge cycles. So when you get into these batteries, these expensive batteries, they actually have a logbook, and some of them and some aircraft will tell you that you're limited to how many start-stop cycles you have, because these batteries do have some inherent problems. Now I have on here memory effect, which I don't know about that one. Which when rechargeable batteries first came out, it was always this memory effect thing, and I believe they did have this problem with some batteries, where the theory was if you always used a battery, like you got a flashlight on the wall, and you take the flashlight and you only used it every night to go down the hallway to the bathroom, and then turned it off, and then you used it down the hallway, back to your bed, and turned it off, and then you hung it back on the charger. That someday when you needed to go outside and look for the dog, it would only last about the trip from your wall. Okay, so it built up that memory. It would die like that, so all that was left. So you would always have to do a full discharge and recharge it, and it was all these problems. I don't know so much about that with Ni-Cads, is they do get out of balance. And out of balance means that all of the cells should be equal and discharge the same and then charge up the same. But after a while, this one discharges really fast, this one doesn't. This guy over here decides this plus is now going to be minus and the minus is going to be plus. They'll reverse their polarity. So you got this one guy, he's going backwards with the rest of the band. I mean, everybody's going this way and they decided to go that way. So yes, you get definite imbalance for sure, positively within these batteries. The one for the 727, they wanted me this summer, just charge it up. I was too busy teaching class to really mess with it, so I just put it on the charger and charged it. But then I asked Harry to actually do a actual maintenance procedure on it. And there was like 3 reversed at that point.
Yes.
Yeah, they weren't when I charged it, but as he started doing the discharge, then they started reversing on them and stuff. So
is there something that causes that more often, or is it just something that
it just happens, abuse. So you don't see Ni-Cads put into service for long periods of time. So back the repair station I worked for, we had it's what we did. One of the things we did was we serviced Ni-Cad batteries, and we were doing them, I think, for Citation and maybe Mather, I don't know. But they bring them in with their logbook, and it was like, okay, it's been 1 year or 1,000 or 100 starts, or whatever it was, whatever the aircraft manufacturer wanted. We have to take them all the way down to a discharge 100%. We put clamps on it so they drain totally flat, clean everything, put it back together, monitor them as they come back up, make sure they didn't reverse polarity on us again, and do a recondition, send it back out. So it has to be done like that. The other problem with Ni-Cads is they do have a thermal runaway problem. And the thermal runaway problem that they have goes into the chemistry of it, basically, which I definitely don't have time for. But what causes this thermal runaway is you would see it on a short hop aircraft. Like, let's say an aircraft, a turbine engine aircraft, was flying from here to International Airport. What's that, 2 minutes by turboprop? So, pick up somebody there, fly over here, shut down, unload, start back up, fly over there, shut down. So it's this rapid discharge, rapid charge constantly is going to heat up the battery. So you heat up the battery and you get a generation inside of there, which starts to break down the cellophane member. That starts to break down, which increases this the oxygenation of the cells, which then increases more heat, and then that creates more heat, and it just starts to run away, and then the aircraft battery kind of melts down on you. So you will almost always see Ni-Cads with a temperature indicator going to the cockpit and a way to disconnect them from the cockpit. So if it does start to do a thermal runaway, you can disconnect it from the system, stop charging it, hopefully let it cool down. So maybe I'll get back into that. Let me see. Construction. Let's see. Picture's worth 1,000 words here. So here's our Nicad battery. Nicad battery. So you lift the lid off, and I don't think I have a picture of that. Let me see. And inside are all of the cells that you guys are actually seeing in the lab. Individual cells. You can take one out, put a new one in. So if you have one bad cell, just buy a new one. Put it in there. Right? You can see here the connection right here. So it's got a quick connect on it. Temperature probe sensor. All right. So what is the electrolyte? Let's see. In a box, cells are connected with metal straps. The active material consists of nickel salts and cadmium salts. A separator is a nylon with cellophane. The separator prevents the plates from touching and shorting out. So how about my electrolyte? What is my electrolyte made out of? 70% distilled water and 30% potassium hydroxide. What is potassium hydroxide made out of?
Bananas.
You're supposed to be my chemist over here.
Me?
Yeah, you seem really good with chemistry.
Yeah, you do. The real Walter White. I don't know.
I know, I was going to say, it's, watching. All right, since you're not going to help me out, I got to do it myself. Oh, there's the plates. That's what it looks like inside a battery. You have to try and put this puzzle back together. So positive, negative, and so they only go in one way, and they go in tight. So they have these plates on there. And over time, you see this white salt stuff starts to build up. That's the potassium salts building up, and you got to brush that off. So electrolyte, my next slide. No, yes, it is. Nicad Electrolyte is 30% potassium hydroxide, 70% distilled water. There's your distilled water. Potassium hydroxide is, in fact, bananas is where we get potassium.
I was going to say banana.
And hydroxide cookies is where we get the hydrox part. And I've had a lot of classes. What are hydrox? They're
They're actually the OG Oreos.
they're the OG Oreos. They are your Tostios. What movie is that? I'm trying to remember. We are not Tostios kind of people. It's a movie. I don't know. We had Tostios in our house the other day. Okay. Possibly also it is this stuff. I'm not sure. So the students tell me that. I don't even. Yes, this is that's the super battery. So yes, it is in fact potassiums and hydroxide cookies. Likely you will leave this class and remember nothing 3 years from now but the potassium and hydrox cookies, because it seems to be the thing. So, and of course, Arrowhead distilled water. All right. These are the shorting clamps that you actually put on. So when you're discharging the battery, you discharge it to to less than 1 volt, hopefully down closer to half a volt, because these things get really, really hot. In fact, these in this picture look like they've turned blue a little bit, and they think they've turned blue because they've gotten hot. I've gotten burned off those before. You just don't realize how hot they get.
You don't want to drain it down to 0, do you?
Oh yes, absolutely 0. These clamps, I need to make this bigger. Why is it gotta be so small? These particular clamps right here, there we go. Those right there, these are maintenance clamps. So you saw the picture before. So every one of these right here, it's a stainless steel clamp that when the battery gets to a certain level, about half a volt, that you're going to clamp these on and leave it on overnight so that it is dead short, dead.
DED.
All right, where can we do now? So they had the memory effects. So constructions. All right, so you wrote down the distilled water and potassium hydroxide, right?
Yep.
Okay, so I don't have to write that. Let's see, 1, 2.
The memory effect, is that kind of like when the cell phones first kind of came out years ago and it said, oh, you got to charge your battery first before you use it?
No, it was...
And then recharge it, otherwise...
No, it's like I was saying. If you only used it for 1 minute all the time, it only worked for 1 minute when you need it for an hour. So... okay, so the we talked about the fact that you're not supposed to charge Nicads, or we work on Nicads and lead acid in the same environment because Nicads are a base and lead acid is an acid, and the two, in theory, cancel each other out. And that's the official FAA statement, although I don't think that's very true according to readings. The specific gravity. The specific gravity of a Nicad is 1.24 to 1.32, regardless of the state of charge. So if it is always the same, would I do a specific gravity reading on it? No. Why bother? It's going to be 1.24 to 1.32. What if it's dead?
1.24 or 1.32?
What if it's really charged well?
1.32, probably.
124 to 132. Doesn't matter. So there we go. Regardless of state. There is a vent cap on these. Vent cap obviously allows the release of gases under pressure. It's about 10 psi. It's quite a bit, but it does theoretically seal in the electrolyte. Very little gassing happens with these when they're being charged, so you don't need to have the ventilation that you do with lead acid, and that's why these are in sealed containers, and they're fine. You want us to wait for you?
No.
Want me to pause? No? Okay. Is she okay? Let's see. Okay, principles of operation. Now we're going to have to skip that because it's all... Okay, specific gravity remains the same. We got that. Oh, I'll just tell you this. 3. All right. As battery discharges, the electrolyte is absorbed into the plates, which lowers the level. So in some respects, I could almost put a liquid level thing on the side of the battery that says full and charged. And as it discharges, you will watch the water level come down, and as it charges, you could watch the water level go up. So therefore, it is critical that you never add water to a dead battery. Nicad, that is. Of course, we're talking strictly Nicads. Because what happens if I look at it and I go, well, shoot, no wonder it's dead. It's got no electrolyte in it. Because that does happen with lead acid. and I add a bunch of water to my Nicad and then I charge it up, you're going to have Nicad soup all over the place. You try and get that back in the banana. Okay, so never add water to a dead battery. You only do it during the last little bit of charging. You do get hydrogen and oxygen. Water is lost by, I think this is a Q&A. Water is lost by evaporation and overcharging. Gassing. Well, that's a good one. I have to start using that one. Hey, I'm just overcharging. Sorry about that. I have to blame it on the dog. Yeah, no, I'm not. It wasn't a fart. I'm just overcharging. I don't know what to tell you. All right, thermal runaway. The cellophane in the separator keeps oxygen that is generated from overcharging from the positive plate from reaching the negative. So you want the cellophane to keep this oxygen that's generated from getting to the negative plate. Oxygen reaching the negative plate recombines with cadmium and creates heat. That heat creates more oxygen. More oxygen creates more heat. Heat causes a breakdown of the separators and lowers the internal resistance. This allows more current to flow and more heat, more gas. Runaway, or vicious cycling is the actual term for it, vicious cycling, can be caused by overuse of starter. Overuse causes heat, repeated starts in short period, charging too rapidly when battery is warm. FA requires Nicad batteries to have temp gauges, and disconnection of charging source is usually enough to stop the runaway. Don't say I didn't tell you. All right, voltage ratings. Nicad. The open circuit voltage of the Nicad is about 1.28. What does your textbook say? All right, what I wrote. The textbook says 1.25. So there's some variation with temp. But about 1.28, 1.25. Immediately after charging, it may be a little bit higher, 1.4, but it soon settles back down to where it should be, about 1.3, 1.28 if you charge it enough. The closed circuit voltage, the CCV of a Nicad, is about 1.2 to 1.25. And of course, the CCV, the constant current voltage, if you plot it out, and you guys will, it remains constant all the way until it nearly dies, and then it just falls off a cliff. Most Nicad batteries, by the way, are about 24 volt.
Yeah.
How could you not tell that that's his variation? UURIGTION, variation. All right, let's see, maintenance. It's very similar to, well, what are you going to do if you have to inspect a Nicad battery? Leaks, cracks, corrosion, leakage. All right, they often have their own log, but inspection is otherwise similar to a lead acid battery. Cracks, leaks, corrosion, distortion, venting system. White powder is what you're going to see on them often. So leak could show as white powder as the liquid evaporates. Obviously, if you're brushing the top of, the top of a Nicad battery, use a nylon brush and not a steel brush or a conductive brush for obvious reasons, or your brush will get red hot. Did I say never add water to a discharged battery? Okay, what do we clean spills with? Boric acid or lemon juice or vinegar or a 3% acidic acid. So why are we using acid suddenly? It's the opposite.
Because Nicads are base.
Right, so we need an acid to clean it up. So we're going to clean spills with an acid. Just pour some lead acid battery on it. I mean, really, don't do that. All right. If a cell does develop a leak, you got to take all of this apart and get down there. You can't just wipe the top off. So, see, I already said that. The only way, just to make sure I do say that, the only way to tell since we can't use specific gravity to tell if it's good or bad, like we can with lead acid, there's only one way to tell what the state of charge is of a Nicad, and that is to discharge it and see if, yep, that thing was fully charged and would have worked. That's the way it is. So the only way to do it is to do a measured discharge down to 1 volt. So it's a measured discharge to 1.0 volts, and that is considered the dead spot. So once it hits 1.0 volt, no point in timing it any longer. Just got to get that 1 volt. So you're going to see how long it takes to do that. And again, that is actually really common now, even in lead acid, to do that as an annual inspection to make sure that it is in good condition. Did I do it? 5, 6. Yeah, we talked about out of balance, memory effect, reconditioning. We talked about C rate. Woo. The most common C rate for Nicad batteries, if I had to just pick a C rate, it's the 0.1, the C.1. So if it's a 60 amp battery, I'm going to put how many amps into it? 6. For how many hours? 10 hours. The other great thing about Nicads is the storage. So how long can I store a lead acid battery dead without problems?
Not very long.
Not very long is the answer. You're going to kill it. So storage of Nicads can be stored dead with no issues. And it can be charged and can be charged for 6 months without loss of power or loss of charge.
That depends on temperature, but it was like super hot.
It could. I don't know for sure. Okay, that was an awful lot, but I think we did it. So we have 10 minutes.
How long do these batteries typically last? Like, like normal car battery or the lead acid ones seem to last.
Gosh,
6 years
you
is
know.
like the end of the battery.
Oh, you're not going to get 6 years out of the lead acid.
Oh, yeah.
Especially because most pilots don't use their airplane very often. Once every other month or something. So the more you use an airplane, the longer it's going to last. Nicad, I don't know, because if you recondition it, you're only changing parts inside. The case is going to stay with the airplane for a very long time, and you're just slowly changing out cells. So it's not like you just have to stop and go, oh, I need a whole new battery. It's like, well, why? Just change out some cells are here, if you do it right. So, okay.